problem that we ran into is that it passes the F-test. So the model, we did the regression and we checked the confidence interval of each of the 3 parameters, and all 3 parameters were 0. But the model is still passes the F-test. So this is a contradiction. And this contradiction comes because we have put just too many variables in there. And that is the problem of multicollinearity. And so the multicollinearity is that if you have 2 lines which are basically the same lines, they have the same slope and the same intercept, and so you don't need 2 dimensions to represent these lines. You could just have 1 dimension, which is that dimension, right? So that's the kind of thing. You are having 2 predictor variables when you don't need 2. You could have done with 1 because the second one is same as the first one. It is just linearly related to the first one, perfectly linearly related to the first one. Okay? So you are making 2-dimensional problem out of a single dimension problem. There is only 1 predictor variable and you are making 2. The same thing applies to you have only k predictor variables and you are making k plus some more number. So you are increasing the dimension, and by increasing the dimension you get into this kind of trouble. So the 2 lines are not independent, and the 2 predictor variables are not independent. They are linearly dependent and they are collinear. That's why they are called collinear, and that's why you get into this problem of multicollinearity. And because of the high correlation between the 2 variables, it's better to remove 1. And so that's the issue, is that when you have a number of variables, one of the things you want to check is, what if I removed some variables? Would the model become better? And that's what might happen in this case, is that if you remove 1 variable, the model might become better. So more variables does not mean better model. All right. So what we are doing in this example is taking the correlation between x1 and x2. So remember, there was, what we wanted to predict was the disk memory and CPU data, right? We were predicting the disk as a function of memory and CPU. And so now we are taking the 2 x1 and x2 variables and taking the correlation. The correlation is 99.47%, 0.9947. So they are basically the same variables. Right? And so that's why you could put almost any values for those parameters and they will compensate for each other, x1 and x2, because they're linearly related. And so the correlation is high. Programs with large memories have large IOs, and therefore CPU time. So that's why basically we were actually predicting CPU time. So CPU time is basically all we need is one of those 2. So you can either one but not both. So these are 2 lessons. If you add a predictor variable, it does not always mean a better regression. Okay, I can replace the word regression with model. Adding too many variables does not improve a model. Okay, and we will see other models later on. Because if the variables are correlated, it may reduce the statistical accuracy. In fact, it may be bad. So one of the ways is that you could try all possible 2 raised to k subsets. So if there are k predictors, if there are 4 predictors, you can write down a table 0, 0, 0, 1, 1, 0, 1, 1, and all that. So you'll get 16 rows. There are 16 possible subsets of the predictors. And you can see the one which gives you the best results with the smallest number of variables. So that is one thing, is that one way, and this is true for other models as well, is that you want to minimize the number of parameters to indicate the model. If suppose you can do something with 1 parameter, why put 2? right? And so that is one thing, is that you want to minimum number of variables. If you have less variables, you have less number of parameters. And the correlation matrix for the subset should be checked. And then whatever you left with, you should see how correlated they are, the axis. Yeah.
This is 2 to the k minus 1.
2 raised to k minus 1?
Because if you choose none of them, you don't have a model.
Yeah, you have model. Actually, model is summarized by a single number, which means no predictors. And so that would be basically what it is that's a model too, is that something is totally random and you don't know how it works.
Okay.
Right? And then you have a model in which the predictors are 0. And you are going to summarize it with a mean or something like that. Right? And so all other models, actually the rest of the 2 raised to k minus 1 models, what they are doing is they are comparing themselves to this model which was there before they were there. That's why we call it SST, the total sum of squares. Total sum of squares is y minus y bar squared. Total sum of squares is sum of y squares minus whatever y bar. So that is the model. Y bar is the model. The model is that they are just going to do with this. All right. So yeah, I mean, technically speaking, that can be called a model, or that could be called no model. But it's a null model.
Or maybe it's completely different other predictors that you didn't use.
So I mean, what you're saying is these are the k I'm using, but there is some other k set. Oh well, I mean, in that case you have 2 k sets. I mean, see, thing is, so first we do is we make a list of parameters, and then we select the factors out of those parameters. So we know there are a lot of things which affect, but we are not going to worry about them. Right? And so if you already know that there are other things that affect, those are in your list of parameters, and you already take a subset of those to call predictors, and then now you are going to subset more. So yes, here k means all of those that basically you decided to use. I mean, if you give up these k and then go for something else, then you will have to do the same thing over there. Okay, so now this is the homework. Result of multiple regression based upon 9 observations. So are shown in the following table. So this is just the output. 9 observations, and you get that B1, B2, B3, B4. There is no B0 here. So B0 through B4, coefficient of multiple correlation is 0.95. Right? That is the R squares. And then this is the F value. Standard deviation of error is 12. So SE is given. This is B0 right here. Okay, I was thinking where is B0. So this is the B0 intercept. So there are 4 parameters, and this is the intercept. So now if you know the standard deviation of errors, you can figure out the degrees of freedom and get the confidence intervals for each of these. And you can see whether it passes the F test and whether any parameters are 0. Right? So based upon the results, answer the following questions and show computation to justify your answers. Just don't answer yes or no. Please tell me why you say yes or no. What percentage of variation is explained by the regression? All right. Is the regression significant at 90% confidence interval? So this is the F test. Is the regression significant? This can be answered by the F test. Which variable has the highest coefficient? Just numerically, Vj. This you can see right now and answer that one. Which variable is most significant? Now this is a statistical question. That means most significant means that at the highest level of confidence, you can do that. Which variable's coefficient is significant at 90%? So some of them will remain significant 90, 95, 99, but at 90%, which one of those? So this is not one variable. Which variables? So basically the quotation marks would be after S. Which variables coefficient are? Okay, so this sentence has to be put into plural. Okay. And then what is the problem with this regression? So you will find out that the F test and the confidence intervals are contradictory. And therefore, just write down the slide 1523 in some place. And then what do you try next? So now you know that there is a problem of multicollinearity. So you have to do something.